Welcome to Inhale's discussion of aerosol deposition and airways for clinicians. As healthcare providers, we're frequently called upon to assist our patients with lung conditions, many of which are caused or triggered by inhaled agents. We also prescribe medications to be delivered by the inhalational route. Our goal with this video is to provide you with a little background in aerosol science so that you can better understand how small particles travel into and deposit into the lung. It's our hope that you will find this both interesting and relevant to your practice. Understanding some of the physical properties of aerosols helps us better understand the spread of contagious respiratory infections. It's also important for understanding exposure to multiple other environmental substances, such as allergens, secondhand tobacco smoke, and air pollution, all of which can trigger chronic lung conditions like asthma and COPD. In some of our other videos, we will see how aerosol science is relevant to understanding the benefits and limitations of different devices used for inhaled drug delivery. So I'd like to briefly mention that I do not have any financial relationships with any pharmaceutical companies or respiratory equipment manufacturers discussed here. Where possible, I've tried to utilize generic drug names and use non-branded visual images. Some of the slides do include references to brand name drugs or show brand names in images. This is either from the source material used or included to help clinicians connect concepts to brands they may know. Importantly, Inhale does not endorse or promote any particular drug or product. The lung has a very large surface area, estimated at 80 square meters, or approximately the size of a tennis court. This design allows for efficient gas transport and transport of small solutes into the bloodstream. Of note, cell membranes and tight junctions between cells form barriers against larger molecules, like proteins, from entering. An adult will move about 6 liters per minute of air across the surface area of the lung at rest, much more during exercise. And if you'll remember the formula, minute ventilation is equal to the respiratory rate times the tidal volume. So the implications of all this are that we have huge exposure to environmental triggers, as well as a huge opportunity to deliver therapeutics. So what's in the air that we breathe? Air is predominantly made of gases, about 78% nitrogen, 21% oxygen, and carbon dioxide and other gases make up a mixture of less than 1%. The rest is made up of water, which can be in any state, gas, liquid, or solid, volatile or semi-volatile chemicals, and airborne particles, also known as aerosols. Some important facts to know about aerosols are that aerosols vary in size, but size is not stable. Size can change as particles stick together or break apart. Size can also change by degree of hydration with water vapor. This is a concept that will come back later in our video that discusses dry powdered inhalers, or DPIs. DPIs are manufactured as a particular particle size, but if used in a humid environment, the particles can swell or stick together, which changes how they travel through the respiratory tract and where they will land. It's also important to note that aerosols vary in composition. They can have an inorganic or an organic core. Aerosols can have metals or other chemicals adhered or incorporated into them, and at times these are chemically active. They can also carry organic materials like viruses, allergens, and bacterial components like lipopolysaccharide or LPS. And they can carry medications and other therapeutics. This graphic provides some perspective on the relative size of different tiny particles. Starting on the far right, a human hair is typically about 50 to 150 microns in diameter, with a grain of fine beach sand pictured next to the hair, measuring on the larger side of this size range, about 90 microns. Moving from right to left, we then see a variety of larger particles with a red blood cell seen in the center of the image at about 7 to 8 microns in diameter. Now, if you focus on the translucent round sphere to the left of the red blood cell, This is a respiratory droplet of about 5 to 10 microns in size. This is the size of an inhaled particle that would be expected to make it down into the lower respiratory tract. All of the particles larger than this will typically be filtered out in the nose and the throat. It's only particles this size or smaller that will travel to the lower reaches of the lung. Inhaler and other medication delivery devices are designed to generate particles this size or smaller, specifically so that the medications can reach the lower airways. It's important to note that respiratory droplets can carry smaller particles within them, which is how many respiratory viruses, the smallest particles shown at the far left, are often spread. Now, this next image shows a subset of that same information, but focusing on the relative size of dust particles relative to the human hair. What I think is helpful about this image is that it also conveys that as particles get smaller, more of them fit into a given volume of air. So, for example, the human hair is approximately 50 microns, and you can see that they have depicted a string of 5 little blue spheres representing coarse particles, or PM10, in the inset photo, and you can see 4 little red spheres representing fine particles, or PM2.5, that can fit into 1 coarse particle. So, as the particles get smaller, the number in a given volume of air increases, which typically means increased surface area of the particles will be available to interact with the airways. Now, the location of where a particle will land in the respiratory tract also depends on the mechanism by which it is deposited. The 4 main physical mechanisms for particle deposition are impaction, where the aerosol is propelled with force onto the surface of the airway; sedimentation, where the aerosol drifts into the lower airway and then settles on the airway surface due to gravity; diffusion, where an aerosol travels based on random movements down a concentration gradient; and electrostatic deposition, where a suspended aerosol is attracted to the airway wall by an opposing electrical charge. We'll talk about all of these in a little more detail. Impaction is the predominant mechanism by which larger particles deposit. Larger particles are trapped in the nose and mouth and upper airway. These are particles usually greater than 10 microns in size. As the stream of air changes directions at branching points, larger particles will hit the walls and the carinas. Gravitational settlement is the primary mechanism by which smaller particles, less than 5 microns, are deposited, usually in the smaller airways. Inhalers with smaller, more uniform particle size will have increased deposition in lower, smaller airways. When using an MDI or an inhaler, the breath holding after the inhalation of the aerosol particles helps deposition in the small airways due to settlement. It's important to know that particles 2 to 10 microns in diameter are preferentially deposited onto the tracheobronchial epithelium as opposed to the nose and the throat. Diffusion is the process by which very small particles, those less than half a micron in size, move from areas of higher to lower concentration. This leads to random collision of aerosol particles with airway walls. Diffusion is responsible for only a small mass percentage of total lung deposition. Breath holding after inhalation also improves diffusion. Without it, particles are likely to be exhaled before they interact with the airway wall. Know that particles between 0.5 and 2 microns in diameter are preferentially deposited in the alveoli, often by diffusion. It's also important to recognize that particles smaller than 0.5 microns are not retained in the lung and are typically exhaled. Electrostatic deposition occurs when particles are attracted or repelled from the airway walls based on their electrical charge. This mostly comes into play for larger particles in nasopharyngeal deposition, but it can also influence subregional location of deposition. As particles become humidified, charge dissipates. Overall, this is a minor contributor to lung deposition. So where do particles land? Many larger particles, greater than 10 microns, are trapped in the nose and upper airways as a result of inertial impaction. So the principle is that the inertia of a particle in motion causes it to maintain its original direction for a certain distance, And as the stream of the air changes direction or velocity, the larger, more dense particles hit the walls of the airways and get deposited. Meanwhile, smaller particles are deposited more by gravitational settlement, which is again dependent on the size and the density of the particle. The much smaller particles from 0.2 to 2 microns reach the alveoli, and particles less than 0.2 microns are exhaled back out. So besides particle size, there are other factors that influence deposition of particles. We've mentioned some of these, which include electrostatic charges, flow rate. The greater the flow rate, the greater the impaction of particles, changes in size of particles, such as hydrophilic particles, and changes in shape and aerodynamic properties of the particles themselves. It's important to realize that the size of pollens allows them to be deposited in the upper airways. Patients with allergic asthma have associated inflammation in the central airways with less pathology found in the gas-exchanging areas of the lung. Another particle that's relevant to lung health is asbestos. The typical size of asbestos fibers is 0.1 to 10 microns in length, a size that is not generally visible to the human eye, but which can still impact the lungs significantly. In summary, we've discussed today how the particle size and the physical mechanisms of deposition are key factors for determining where an aerosol will land within the respiratory system. And knowing where an aerosol will land is important for predicting where it will have its effect, whether that's the therapeutic effect of a medicine or an undesirable side effect or an exposure. We'll see that this will become very important for understanding the different delivery devices for aerosol medications. Questions we'll want to ask when selecting a delivery device for a patient include: what size particle does this device generate? And are the particles that it generates uniform in size or a heterogeneous mixture of sizes? How is the aerosol released or propelled from the device? And will this cause a lot of impaction in the pharynx or allow the aerosol to remain suspended and travel gently to the lower airways? Does the inhalational technique used with a specific device allow time for sedimentation and diffusion to occur into the lower airways? So from all of us here at the Inhale team, thanks for watching.